Thank you. So let's talk about time scales. So this is a log scale. Each tick on this chart is 10 times the value to the one to the left of it. We've got nanoseconds on the far left and millions of years on the far right. Now, normally when we talk about software, we're talking about the far left side of this chart, because computers are fast. Processor and memory operations are measured in nanoseconds, disk and network in milliseconds. If a computer takes a second to do something, we start getting impatient. This middle of the chart here, this is the human scale time. Our threshold for perceiving that one thing happened before another is around 100 milliseconds. Our lifespan is roughly 100 years. But we can talk about software in this scale too. Software is by and for people after all. We track work in terms of hours and days and weeks, product life cycles in months and years. Right about here on the chart, that's how often there's a new JavaScript library that we're expected to have an opinion about. And this spot here, this is how long we've had computers. My grandparents are older than that. In terms of human endeavors, software is a profoundly young field. And because software is such a young field, we don't really think about the right side of the scale here, the years and decades and centuries and so forth. I mean, I understand why. It seems impossible to even conceive of software on these time scales when computers advance so quickly. But I think this is a mistake. Now, as web developers, we tend to think of anything older than 6 months as legacy code. But there's tons of code from the 60s and 70s that's still running today, and the design decisions made back then are still reflected in contemporary systems. There's no reason to believe that software can't live for 50, 100, 1,000 years. Anyone in this room could be working on a project that has that kind of lasting impact. So today we're going to talk about software on that long end of the time scale and what it takes to make a program last. So we'll discuss bit rot and why software can never be done. How programs adapt to their changing environments and their shearing layers models of growth. The lessons of COBOL and the world's oldest running computer program, and the mistakes we make that can take years or even decades or centuries to surface. Now first, let's talk about bit rot and the paradox of software decay. Now, physical artifacts decay. Wood rots, plastic cracks, metal rusts. Parts wear out and break and need to be replaced. Machines demand maintenance. This doesn't happen in software because bits don't literally rot. A function will not wear out no matter how many times you call it. Computers can break, but software is just information. Software can be eternal. But on the other hand, there are all sorts of circumstances where software will stop working. This happens a lot on the web because everything is so interdependent. Links break, servers crash. Twitter buys a third-party API service and shuts it down 30 minutes later. Too soon. This is a huge pain point with IoT devices. Your smart home hub and all your robot lights still work just fine, but the service that allows all of them to communicate has been shut down and now everything's useless. Now, even if your web app is totally self-contained, it still depends on the user's browser and computer, and that can break your software too. Now JavaScript has suffered a lot to remain fully backwards compatible with whatever design decisions that were made by Brendan Eich or design non-decisions that were made by Brendan Eich in the early 90s, and things like Smushgate this was a couple months ago now. There's this whole controversy over how adding a flatten method to arrays would break websites that use this 8-year-old version of MooTools. And rule 0 for adding any new browser feature is don't break the web. Except that rule gets broken all the time because browser vendors, to some extent, have to break the web. I mean, if you think about it, the whole point of any new security feature or ad blocker or anything like that is to break people's software. The hope is that we're only breaking bad software, but it's still breakage nonetheless. And the shift to mobile over the last 10 years has broken a lot of software. It's really quite impressive that, the early mobile web experience worked at all. In some ways, I am grateful for this. I owe my career to, Flash dying, because a lot of my work when I was getting started was rewriting websites to be more mobile-friendly with media queries and changing the Flash stuff to JavaScript. On the other hand, it's hard to feel good about anything that prevents people from seeing Homestar Runner cartoons. Right on! Now, here's the paradox. Software is information, and information can live forever. But doing anything with information, extracting meaning from data, is wholly dependent on context. You cannot make sense of a message if you don't speak the language or if the message presumes some sort of background knowledge you don't have. Likewise, you can't do anything with software if it presumes things about the computer it's running on or the network it's connected with that are no longer true. You can preserve data forever without it ever changing. Preserving meaning requires continuous change. Now, so preserving software requires continuous adaptation to shifting contexts. Now, when I think about this, I don't necessarily think about software. There's a book about architecture that's shaped a lot of my thinking around this. It's called How Buildings Learn. It's about the qualities that are present in, a lot of it is unremarkable industrial buildings that nevertheless make them valuable and useful for hundreds of years. And like software, buildings need to evolve over time if they're to remain useful. Buildings require physical maintenance, of course, but buildings also have the problems of shifting context we encounter in software. People come to expect running water, electricity, air conditioning, Wi-Fi. Software has GDPR compliance. Buildings have ADA compliance. Manufacturing leaves town and the old textile factory turns into this is the Loom, which is basically a hipster mall with loft apartments. Now, I don't want to lean too far into this metaphor. I mean, I'm not suggesting that you repurpose old insurance software into luxury condos, but the idea from this book that has served me well in dealing with legacy software is this notion of shearing layers. Because most buildings are not monoliths, they are networks of interconnected but still discrete systems. You know, some parts rarely change. It's not impossible to move a building, but it rarely happens. Location is essentially a fundamental property of a building. And some parts change all the time. Furniture is meant to be moved around, reconfigured, and replaced. Like one of the bits of wisdom from the book is that, like, well, the Italians call furniture mobile, and that's because you can move it around. And in between these, you have these other systems and structures, like interior walls and HVAC don't get moved around every day, but they're not intended to last forever. They are understood to be impermanent. Exterior facades, they're exposed to the elements, and they need to be replaced periodically. And the structure of the building, like the foundation itself and the load-bearing walls, those last a lot longer than the other parts, and because they're far more expensive to replace, they tend to change rarely. Now, to be clear, this is a description of an ideal building, but not like every building. You'll see violations of this shearing layers model across the board, from single-family homes to like Frank Gehry sculpture buildings. Often the more upfront design that goes into a building, the less able it is to adapt to future changes. You can't move furniture around if it's like built in, and it's hard to add an addition to a building when there are no flat walls. It's also important to distinguish the critiques of like specific modern buildings from complaining about modernism or novelty in general. I mean, lots of old buildings violated these rules too, but those buildings didn't last. The reason these qualities are present in older buildings is it's pure survivorship bias. The qualities that promote longevity are the ones that are still around. Now, the software engineering equivalent to this model is the notion of high cohesion and low coupling. Code is organized into components with a single purpose, and these components interact only through well-defined interfaces. The idea here is that if you make a single change to how the system functions, you will make that change in a single component. Now, you might be a step ahead of me in trying to figure out like how you would map this exact model onto software. Like, what are the shearing layers of a web app? And I think like a lot of our conventional wisdom would say something like, oh, so we've got like styles at the top, and then the language at the bottom, and then all these other layers. But I think that one of the problems that we as web developers are facing today is that if you try and apply the conventional wisdom to a modern web app, you'll very quickly see how all the layers don't quite shear the way you would hope. I didn't introduce this model like 5 slides back just to pull the rug out from under you, but I think that one of the core problems in modern web development is that web pages and web apps, they break apart in totally different places. For example, in page-oriented web design, we have this divisions between content and presentation, which handily maps onto HTML and CSS. The divisions are fairly clear. The document and styles are independent entities. The HTML carries the information. The CSS manages the presentation. If you're writing a new blog post, you don't need to also create new styles for that post. And if you're changing the website's theme, you don't need to rewrite your old entries. The document and the styles can change independently, and the styles and markup are discrete shearing layers. But in app-oriented web design, the divisions are much less clear because there's no single document in a web app. There's lots of little bits of information all around the page, surrounded by interactive elements. Most of the HTML that we write is not intended to be read like a book. It's intended to be analyzed like a diagram. And our experience with writing app-oriented code is that CSS and HTML tend to change together, not separately. They have high cohesion. The separation instead happens at the component scale. And I think this explains why in the apps that I work on, the legacy code that I guess fear the most is in the old style sheets. Not because I dislike CSS as a language or I don't understand the cascade, but because the styles weave throughout my code. They don't respect the boundaries of my components. They follow a completely different structure. The idea that unites a lot of the new CSS systems, like CSS and JS, scopes, style sheets, views, single file components even, is that styles and markup belong together because they change together, and combining these concerns within a component allows greater separation between components. This separation makes it just a little bit easier to add and remove and change and rearrange stuff without worrying about something subtly breaking something else. This sort of separation is what allows longevity because it allows change. I realize that I've given this talk a couple of other places before, and this is like the most preaching to the choir experience. I can think of few audiences that would be more receptive to hearing that collocating styles and markup make change easier. Raise your hand if you maintain a library that does this. Okay, but yeah, most of us only see change on this months to years scale. What does it even mean for a program to evolve on the decade plus scale? So let's talk about COBOL and the world's oldest running computer program. Now, this is a question I like asking. Anyone here ever write COBOL for work? I see a handful of people. There's always a few. The first time I gave this talk, I saw 3 hands go up. One person who said they were doing it in the 70s, like when it was originally a thing. One person who was doing like Y2K remediation in the late 90s. And one person who's like 25 years old and I'm like, what are you doing, man? It's like, I don't want to talk about it. So COBOL, the Common Business-Oriented Language, is one of the oldest programming languages still in use today. It's from like early 60s. Now, business-oriented in this case means that the math features are built for accounting and not science. There's a lot of built-in support for processing text and database records, or like a lot of support for the 60s. One thing that is maybe wasn't unique about COBOL then, but is now unique about COBOL is that it uses fixed length numbers instead of floating point, which makes it still has native support for fixed length arithmetic, which makes it surprisingly still useful for like the IRS, where they're dealing with money and they don't want to have like 0.030000004 cents. Now, most importantly, COBOL was one of the first languages that was designed to be sort of readable, if not necessarily writable, for non-programmers. It wasn't entirely successful at this. Every generation thinks that they've invented like the programming language that doesn't require you to know how to program, but this was still probably an improvement over like machine code. Now, COBOL is not a well-liked language. This is the jargon file entry on COBOL. No self-respecting hacker will ever admit to having learned the language. Its very name is seldom uttered without ritual expressions of disgust or horror. Ritual expressions is like contempt culture has been with us for a long, long time. But here's some facts about COBOL. It was the most used language in the world for like 20 years. A huge amount of COBOL software is still in use, particularly in critical infrastructure, and the oldest software still running today is written in COBOL. And that program is called MOCAS, short for the Mechanization of Contract Administration Services. It's used by the Department of Defense for tracking contracts and payments to vendors. It was originally written in 1958 in a language called Flowmatic, which was, I guess, sort of like a proto-COBOL, before its standardization, developed by Grace Hopper for the UNIVAC one, both pictured here. Of course, MOCAS has changed a lot since 1958. I mean, just think of how much computers have changed since 1958. The UNIVAC, as its name suggests, used vacuum tubes instead of transistors. In most cases, only the sysadministrator would actually sit at this console to interact with the computer directly. Everything else was batch jobs. Adding a contract or running reports on this system would have involved you'd hand a stack of punch cards to the operator, and they'd drop into the computer, and you get a printout of your report, printout of the results the following day. But in the mid-60s, computers could be used interactively via teletype, as pictured here, and multiple users, the magic of time sharing. The sea change led to Mocus being ported from Flowmatic, which ran on only the UNIVAC one, to COBOL, which is a standardized language that was, while largely derived from Flowmatic, ran on many different computers, such as the IBM 360 right here. At some point in the 70s, it was updated again to be used with the sort of green screen terminals that one can still see in underfunded public libraries, or I suppose any web developer's console. The user interface of the program was changed completely, but the core business logic remained the same. And the system continued to adapt throughout the 80s and 90s and aughts and today. I mean, nowadays, to Mocus to its end users looks like a typical corporate intranet application. You access it through desktop PCs. You can attach Word documents and Excel spreadsheets, because, I mean, that's how people do contracts today. But it's recognizably the same program now as it was in 1958. It's still essentially a CRUD app for managing invoices. And the Department of Defense has tried many times to replace this system wholesale with something new, but it's shockingly hard to justify throwing out something that works, even if it's old-fashioned or even archaic. It works well enough for its given task, and at any given moment, it's faster and cheaper to just hack in the next feature instead of starting over from scratch. As long as IBM keeps selling them hardware that can run it, Mocus will still keep processing contracts. Now, I think there's a lot of parallels between COBOL and JavaScript. Every mean thing that people say about JavaScript was said about COBOL 40 years ago. In both cases, a lot of it is accurate. But just as COBOL ran on every mainframe and mini computer back then, JavaScript runs on every computer of whatever size today. Likewise, I think we can expect JavaScript to have a similar lifespan. Even if every new project from here on out is written in Elm or whatever, there's still a massive amount of JavaScript code out there today that will stick around as long as it's cheaper to hack in an update than rewrite it from scratch. So where do things go uniquely wrong in legacy software? What are the kinds of problems that only surface on that decade scale? Now, I mentioned the layers and boundaries earlier, and a lot of the problems we encounter on the months to years time scale are violations of these constraints, like view code that talks directly to the database, that sort of thing. I mean, we struggle with this, but hopefully we know when we're painting ourselves into a corner, we recognize that when we are accruing technical debt. The problem that really kept us off guard happened on this decade-plus scale, because I think there's something in programmer psychology that makes us think that surely by the time that this would be a problem, that code will be long gone, the company will be out of business, or more often the case, I won't be working there anymore. And this mindset has been with us for a very long time. For example, here's some to-dos from the source code that ran the Apollo 11 guidance computer. I mean, it worked. They got to the moon. Now, the canonical example is the Y2K bug. In the 70s, so it was common to store date formats, and dates in a format where the year was represented as just the last two digits. The saved space when every byte counted. But even back then, people knew this would eventually be a problem. The COBOL style guide from 1970 warns programmers to use 4-digit dates. But people ignored this. They figured, somebody else will come around and fix it before it becomes an issue. And this continued until 1997, when it dawned on us that the somebody else is me. And a bunch of the programmers who had originally written the software back in the day found themselves put back to work updating systems to use 4-digit date representation and charging outrageous consulting fees. But we've only really kicked the can down the road a few years, because Unix timestamps are 32-bit signed integers and will roll over in the year 2038. Now, most systems use 64-bit timestamps, and most languages and libraries support this, but there's still tons of code out there that's using 32-bit timestamps, especially on embedded devices, all the tiny machines that run our society. And there's been a couple of minor 32-bit integer bugs that have already bitten us. One that sticks out for me is a few years ago, APU's play count for size Gangnam Style rolled over into negative numbers because they went over 2 billion plays. I've seen a couple of services go down for hours or days because they used 32-bit ints for database IDs and ran out of space. 2 billion is uncountable for a human, but it's still so much closer when you think, especially when you're operating at Facebook scale. But the more insidious bugs are the ones that are data modeling bugs, because the ones that are in the assumptions we make about how society operates and will operate in the future. So, I mean, I found this code example just by doing a Google image search for COBOL. And I actually was able to find the rest of this program. This is just demo code for explaining how to do multiple clauses and conditionals, but just look at how many assumptions about society how society is governed are encoded into this short block of code. I mean, like the age of majority is this, 18, this magic integer, and the human gender is representable as M or F, and anything else is literally invalid input. Now, maybe you're willing to cut 40-year-old demo code some slack, so here's a real-world example with those same assumptions baked in. This is a dashboard my team made for showing demographic data. This page has an important but fairly small audience, and our team was dissolved shortly after we shipped this, so I know this isn't going to be getting a lot of updates in the future. Now, I mean, I'm already kind of suspicious about how meaningful any sort of demographic advertiser data, and maybe advertising statistics is not the place to like fight for representation, but it still bugs me that the model we're using here is built on all these assumptions that like this dashboard reflects a world that one would hope is disappearing. It's a world where gender lines are this sharp divide where it's even, regardless of like the notion that like male and female audiences are like meaningful divisions, that like male and female audiences like the only genders, and also like the other one that I think a lot of programmers forget is like the ageism encoded in this is like your usefulness as an audience ends when you're 65. I mean the dashboard launched we launched this spring, in so many senses of the term. There's already so much like legacy code in here. So the title of this talk, 100 Years of JavaScript, it is intended to read as a threat. But I would frame it as a responsibility, it's a call to action. On one hand, it's deeply optimistic to think that any of our code will matter in the long run. I mean, there's days when I wonder if I should be preparing for a different kind of world. I wonder if, I wonder how long it'll be before like I no longer even remember JavaScript fatigue because I'm trying to learn how to fix small engines and radios. But on the other hand, I understand that I've put something into the world, and I'm responsible for its impact, no matter how long that may be. Now, a lot of programmers, we're just sort of coming to terms with the ethical implications of how our software is being used, or like how the rise of Bitcoin mining has made us so aware of like the direct ecological impact software can have. But we also need to think about like the deep future. What are we leaving for future generations? I mean, will that to-do comment still be in the code a decade from now? Will we have to come out of retirement to fix our equivalent of Y2K bugs? What invisible assumptions and bigotries are we encoding in the software that will be laid bare in a more enlightened time? Now, I think a lot about legacies. I mean, not just legacy code, but just like the notion of legacy in general. Now, for a lot of people here, I think that's like their family, their children. Now, I'm secretly goth AF, and I take sort of a Philip Larkin view of parenthood. But so when I think about legacy, when I think about the impact one's work will have on the future, my mind naturally jumps to nuclear waste. So the problem of nuclear waste is that spent fuel rods can be hazardous for hundreds of years in the future. Materials contaminated by nuclear weapons research can be hazardous for tens of thousands of years. How do you store waste safely for 10,000 years? Now, the physical part of this is actually quite simple. Just bury it under 2,000 feet beneath a salt flat in New Mexico, no problem. The hard part is keeping people out, because 10,000 years is a very long time. 10,000 years ago, we were living in caves. How do you put up a warning sign that will last that long? How do you communicate this message with people that will absolutely not speak your language and may have lives that are incomprehensibly different from your own? I mean, will a skull and crossbones keep people out, or will it encourage people to dig, looking for pirate treasure? Now, with this kind of responsibility, I mean, like maybe we should hope that our work is solely ephemeral. I mean, I've certainly written code that I wasn't proud of. I've written some comments that were basically, it's essentially supposed to mean this place is not a place of honor, nothing valued is here. But all of our work has the potential to outlive us. I mean, we don't have to think about our work like nuclear waste. Maybe there's a positive spin on this. Maybe our work is like forestry, where everything we do is interconnected, and the processes we begin today might not come to fruition for 100 years. Now, this can be a terrifying responsibility, but it's an opportunity to shape the world far beyond our own lifespans, far beyond our like how to we all want to change the world, but like when we realize that we are changing the world, it's so much pressure. But like we have this opportunity for immortality. Let's make our immortality count. Thank you.